Hi guys, welcome to our video. This video is for our assignment DEC 30302 Computer Education and Organization. The title given is Memory Hierarchy. This pair assignment consists of two members, that is Lau Wenquan and Hishamuddin bin Dahil. Without further ado, let's move on to the first topic, that is Introduction to the Memory Hierarchy. Memory is one of the most important parts in computer architecture. Memory is used to store data, program, and instruction sets. Because of that, the most things our memory needs to have are transfer speed, flash capacity, and capacity. The first way to access memory is to use static RAM, but static RAM is much more expensive. So, to provide a larger space for memory, we can use magnetic disk. Magnetic disk provides much more space with reasonable space and speed. There are many types of memory with different speed, cost, and space, but there are memory hierarchy prior to their speed and size. The faster the time to access data from the memory, the better the performance. This is because if data can be accessed in very short time, but the time to execute program or to do operation also can be reduced. Figure 1.0 shows the memory hierarchy. So, from top of the processor until the down of the memory magnetic disk, the size are increasing. However, the speed and the cost per bit are decreased. So let's come to the next topic, that is hierarchical memory technology. Storage devices such as registers, pages, main memory, disk devices, and tab units are often organized as a hierarchy as depicted in Figure 2.0. The memory technology and storage organization at each level are characterized by five parameters: the access time, memory size, cost per byte, transfer bandwidth, and unit of transfer. The access time refers to the round trip from the CPU to the I-level memory. The memory size S is the number of bytes of word in level I. The cost of the I-level memory is estimated by the product CS. The bandwidth of B refers to the rate of information which is transferred between adjacent levels. The unit of transfer SI refers to the range size of data transferred between levels I and I plus 1. Figure 2.0 shows a four-level memory hierarchy with increasing capacity and decreasing speed and cost from low to high levels. So you can see in Figure 2.0, as the level increasing, the capacity and access time are decreasing. However, the cost per bit are decreased. So let's move on to the next topic, that is inclusion, covariance, and locality. Information stored in a memory hierarchy satisfies three important properties, that is inclusion, coherence, and locality, as illustrated in Figure 3.0. Considering the cached memory in the innermost M1 which directly communication with the CPU registers, the outermost level MN contains all the information words stored. In fact, the collection of all addressable words in MN forms the virtual address space of a computer. Program locality is characterized below as the foundation for using a memory hierarchy effectively. Information transfer between the CPU and cache is in terms of words. The cache is divided into cache blocks, also called cache line by some authors. Each block is typically 32 bytes. Blocks are the unit of data transfer between the cache and main memory. The main memory is divided into pages 4 kilobytes each. Each page contains 128 blocks. Pages are the unit of information transferred between disk and main memory. So as you can see in Figure 3.0, it shows inclusion property and data transfer between adjacent levels of a memory hierarchy. So first, the CPU register will access by word from a cache block of 32 bytes / block A. Then it will access by block from a memory page of 32 blocks or 1 kilobyte such as block B from page 8. Then will be accessed by page from a file consisting of many pages such as page A and page B in segment F. Then finally, it will be segment transfer with different number of pages. So the step instruction relationship implies that all information items are originally stored in the outermost level Mn. During the processing, subsets of Mn are copied into Mn-1. Similarly, subsets of Mn-1 are copied into Mn-2, and so on. Information transfer between the CPU and cache is in terms of words. The cache is divided into cache blocks, also called cache lines. Each block is typically 32 bytes. Blocks such as A and B in Figure 3.1 are the units of data transfer between the cache and main memory. Subscriber pages are organized as segments in the disk memory. For example, segment F contains pages A, B, and other pages. The size of segments varies depending on the user needs. Data transfer between the disk and the tape until it is handled at the file level, such as segment F and G illustrated in Figure 3.0. The coherent property requires that copies of the same information items at successive memory levels to be consistent. If a word is modified in the cache, many of the words must be updated immediately or eventually at all higher levels. In general, there are two strategies for maintaining the coherence, that is, write through and write back. The locality of references system memory hierarchy was developed based on a program behavior. The memory references are generated by the CPU for either instruction or data access. These access tend to be clustered in certain regions in time, space, and ordering. There are three dimensions of the locality property, that is, temporal, spatial, and sequential. So, in memory design implications, the sequentially in program behavior also contributes to the spatial locality because sequentially code instructions and array elements are often stored in adjacent locations. Each type of locality affects the design of the memory hierarchy. The temporal leads to the probability of the least rational yield replacement algorithm. The spatial locality assists as in determining the size of unique data transfer between adjacent memory levels. The temporal locality also helps determine the size of memory at successive levels. The sequential locality affects the determination of grain size for optimal scheduling. Research techniques are heavily affect the locality properties. The principle of locality will guide us in the design of cache, main memory, and even virtual memory organization. Now, let's move on to the conclusion. Last but not least, as for a conclusion, memory hierarchy can be divided into 5 major levels. Prior to their seat, there is processor cache, primary cache, secondary cache, main memory, and magnetic disk memory. Usually, processor cache, primary cache, and secondary cache implemented inside the processor while others are located externally. Thank you for watching our video. See you. Thank you.